Okay. So can everyone see the slide, the first slide?
Yes.
All
Yes.
right. All right. I have to make sure that I see the participants. So yes, thank you very much for the invitation, and I will try to give you a review, an overview of an approach that I have developed together with other people too, toward AGI in general, which is a quite great goal and of course a hugely ambitious goal of which I can dare to hope to make merely a contribution, hopefully in the right direction, so that others can pick it up from there and build the full-fledged AGI then. So just let me tell you something about myself. I am basically from Germany, um, a physicist by training, studied there, and then switched to AI, or the neural network type of AI, intermingled kind of in a intermediary discipline like cognitive psychology and neuroscience. Specifically, I did neural network models of cognitive development in infancy because I wanted to know how it all starts with infants and what we can learn from them. And then I moved to Odessa in Ukraine and started the business there, and later on kept thinking about AGI and started a research lab, Odessa Competence Center for Artificial Intelligence and Machine Learning, which has been quite active for 2 years and which is now not so active anymore in the last 1 or 2 years. But I keep pushing forward the ideas and the topics. So the talk is divided in 3 parts. Essentially, in the first part, I want to give you some psychological plausibility of the main ideas, so that you get the big idea first, and then dive into the theory, which gives mathematical guarantees for that the psychologically plausible things are actually true and actually will work out, and where I will present in short ICSI, the Marcus Hutter's theory of universal intelligence, and then my theory of incremental compression, and then in the last talk I will talk about the implementation and actually hands-on result, what actually works in practice. So thinking about cognitive abilities, I mean, it's all quite overwhelming, right? We have creativity, problem solving, pattern recognition, classification, learning, induction, deduction, building analogies, optimization, surviving in an environment, language processing, planning, knowledge, all sorts of complicated things. And formally defining every aspect of intelligence is quite difficult. So, but I would like to put forward a hypothesis that data compression could explain, at least in part, many of the cognitive abilities, or can help actually build a psychological theory and also a mathematical theory for AI using data compression. I'm, of course, not the first one to put forward. It's like it's the data compression school of AI. I'm trying to build it further. So let me give you an example. The very old Gestalt principles of organization in psychology have been put forward like 100 years ago or so to explain some sorts of perceptual effects. For example, in the figure A, you see lines, 8 lines that people tend to group into 4 groups of 2 lines. And the Gestalt psychologist put forward the principle of proximity. If something is close or nearby, then you tend to group it together. Well, that works well for grouping of the objects that are nearby, but for grouping of objects in the figure B, it doesn't work so well anymore, or in other cases. Yes.
Your slides might be not where you think they are. We're on slide 53 right now.
Oh, slide 53.
What's being displayed is your last slide.
Oh, really?
Yeah.
There, you gotta change that.
There we go.
Aha.
Yeah, it was on slide 53 from the beginning.
Okay, okay. Oh, I'm sorry. I didn't know why that happened. So this has been the very first slide. This has been the next slide. And then this is the review: psychological plausibility, theoretical guarantees, and the practical engineering. And this is I've talked through, and this is the current slide.
Okay. Thank you.
Okay. So we see that the lines tend to be grouped together. Well, currently we say that's clustering, right? And we have clustering algorithm, it groups stuff together that is nearby. But what is clustering? I mean, what do machine learning algorithms do in general? And what is too seldomly taught is that much of what machine learning algorithms actually do is data compression. For example, how can we see clustering as an example? Well, you need in order to encode a number n, you need the logarithm of n bits in order to encode it. So smaller numbers take less memory to encode. So if you can take a bunch of big numbers and reduce them to a bunch of small numbers, you have compressed data. So how does clustering do that? Well, you have a bunch of big numbers clustered somewhere, and you replace them by a cluster center and the difference between each of the points to the cluster center. So n big numbers are replaced by n small numbers and one big number, the cluster center. And that's a compressing thing. You need less space, and therefore the cluster center is found. So you can also turn it around. If the compression is your goal, then an algorithm that you will build will actually find the cluster center. So you don't actually need a particular principle of similarity in order to explain this first example. And the data compression is sufficient in order to do so. And you can look also at other examples like in the figure D. And for example, these circles can be described by a center and a radius, right? And where the points where they intersect actually can be derived from their respective centers and the sizes. So in order to encode them, you don't need much space. And why do people perceive one circle as overlapping as the other? Well, in order to encode the arc, which is of the circle on the left, you just need less space if you say that it ends at the border of the right circle. And you can go on doing making other examples, like in the figure B. If you first describe this, the little circles and then describe the crosses and then combine them together, it's compressing better than if you group them in a different way, not by lines but by colors or so. So let me give you another example. How do we perceive letters, for example? Letters can be perceived as consisting of different lines, vertical or horizontal lines, which can be called features. And to just combinatorially combine different features to represent the letter. Or you can say you save templates particular letters, like a ready letter A, for example. It's somehow stored as an image or so somewhere in the brain, and then when an actual letter comes outside, you match them with your template. That's template-based perception. Well, the compression theory says, okay, if you have many letters consisting of those features, then it will be, you will save more memory by storing the features and combine them in various ways. On the other hand, if there are just a few complex stimuli that consist of all kinds of different features, then it might be better to store as template. And because you don't have many, you won't need many templates, and then you can, whatever you see, you can match against them. So the compression theory actually predicts in which cases there will be feature-based perception, and in which cases there will be template-based perception. So that's another example. Let's take an important further example. Let's say you want to perceive various objects like the animals. Psychologists have established that people actually parse the body parts of animals in like in the figure on the top right here. And so you have the neck and the legs and the head. For things for which we actually have words correspond to parts of the animal that into which we parse it actually. So, and the question is why do we parse it in this way and not some other way? Well, consider the example of the giraffe's neck here. And the upper part is called X, the lower part Y, and the body is Z. So should we group X and Y together and leave Z separate, or should we group Y and Z together and leave X separate? Well, if you try to compress data, X and Y actually have a lot of common information. It consists of a cylinder basically going into the same direction. So if you know how to describe X, you can also quite easily describe Y. So in the language of Kolmogorov complexity, that means the complexity of the concatenation of X and Y, which can be considered of strings of zeros and ones. You can encode everything in strings of zeros and ones. So that means that the shortest description that you can find for giraffe's neck, if you group X and Y together, will be shorter if you group it in another way. If you so grouping X and Y together and leaving Z separately leads to a shorter description than grouping Y and Z together and leaving X separately. Because Z points to another direction, looks in practice also differently than the cylinder actually. So the lower and upper part of the neck look more similar to each other than Z. So and you can apply this principle quite generally. And the idea is that the whole part relationships of our world should emerge as a consequence of data compression. That's the whole idea behind this example. And this is one of the examples actually that are part of the argument why compression might be a good idea. So let me skip the more examples because I want to get ready. So the bottom line is I've went through a whole range of examples and basic cognitive psychology experiments picked from different subset of cognitive psychology. topologies of subfields like knowledge representations, memory retrieval, hypothesis testing, developmental psychology, and the psychology of language. And many of the results there could be explained by a unified theory. But of course, I cannot claim that before psychologists have not worked out the details and have actually tested whether it actually works. But it's possible to derive falsifiable predictions, like I've said, in the feature-based versus template-based perception. So let's move to the theoretical guarantees. So these might be plausible things that I have said, but who knows whether this is actually meaningful or works at all in practice. We don't want to just talk, but we want to actually to build a mathematical theory and also want to test whether it works in practice. So what we have is a structured top-down approach. So we start out with the definition of intelligence, which informally can be stated that the ability to achieve goals in a wide range of environments. And if that's what intelligence is, I mean, not everyone agrees on that. People have different definitions. But based on the definition, Marcus Hutter has developed a theory of universal intelligence. And its most famous agent of that theory is called ICSI. And we can view ICSI as a combination of the so-called Solomonov's theory of universal induction and reinforcement learning. And the hard part is that universal induction requires data compression, and that's where the compression ideas will come into the picture. But first, I will tell you a little bit about ICSI and Solomonov induction, and then go to the theory of compression. So what's induction actually? So look at the picture below, you see some boxes or box behind the tree. So how many boxes would people say are behind the tree? Well, most people would say one, because, well, they look like they have the same height and the same color, most probably one. But theoretically, it could be two or 358, right? We don't know. Maybe they are very narrow boxes. And how do we induce, so how we find explanations for what we see? Let me give you another example. If you have a sequence -1, 3, 7, 11, and does it continue with 15 and 19, or with these strange numbers? And well, as you know, we can always fit a polynomial to a bunch of numbers. So this polynomial could also try to predict it. So people involved in machine learning know very well this would be overfitting. And Occam's razor says actually explanations should make no more assumptions than necessary. So the shortest description actually would predict 15 and 19. If you can write a short program that starts from -1 and adds 4, and it will make a prediction. And the code of the program will be shorter than the code for this polynomial. And therefore, in accordance with Occam's principle, we should prefer the simpler explanation, the shorter description in terms of Kolmogorov complexity, in order to explain the data, in order to compute predictions from that. So, formally, Kolmogorov complexity of a string x is a string of zeros and ones usually, or some symbols, is defined as the smallest program that runs on the so-called universal Turing machine that produces x. So L of p is the length of the program, and U is essentially a universal computer. So for people who might not be familiar with it, it's a mathematical model of computation. It has an input and has an output, sometimes, not always. Sometimes the computation doesn't help, and as we know, we can easily program things that go on in an infinite cycle and never helps. And so the Kolmogorov complexity is defined as the shortest description of the string. So, and let me introduce you in one slide to very quickly to Solomonov's theory of universal induction. This is important because this relates to how we find explanations of our world. How can we explain what happens around us and make predictions what will happen when we influence that world? And the question is, well, do we have a mathematical model of prediction? Well, it turns out Solomonov induction is the best predictor there is that exists at all. It can predict anything that is predictable, so to speak. And so how does it work? Let's consider a string x consisting of zeros and ones. So x1, x2 is either a 0 or a 1. And let's take the notation from x to 1 to t is that string. By the way, can people see my mouse, or is it not possible?
Yes, we can.
Okay, great. And the so-called Solomonov prior m of x is defined by the sum of all programs that run on a universal machine that produce the string x, weighted by the 2 to the minus of the length of the program. So what does that mean? Let's take a simple example. Suppose x consists of a string of zeros. That means that a short program will exist that prints that string of zeros. Right? You can write a simple loop in a one line, and that prints a string of zeros. So this program is q, and the length of the that's L of q. So it will be quite short. And therefore, this factor L to the minus L will be large. And so the Solomonov prior will be large. So that means for simple sequences, the prior will be large. But what does it mean? It says that, okay, what is the a priori probability that I will see something simple? Well, Solomonov's theory said, oh, it's large. And the a priori probability that I will see something complex, like suddenly the whole world around me turns into some white noise, right? In some to a broken TV screen. And so the Solomonov theory says, oh, the probability is low that this kind of thing happens. And and it turns out that this prior is quite good for making predictions. I think I should not go deeper into that, because in order to be in time. So the end of the slide essentially shows that for any sequence that we see here below, if you see a prefix of a sequence up to index t, the probability that the Solomonov prior will predict the right continuation of the sequence will go to 1 as the length of the prefix increases. So the more we see of the string, the better this predictor can predict what will happen next. So in that sense, it's the best predictor there is. And it shows that it actually predicts well, but in another proof that I have not shown here, you can show that there is no other predictor that predicts sequences better than Solomonov's prior. And now here, the important part, the 2 to the minus L, is actually the compression part. So you have to find programs that are short in order to approximate this expression, because the shortest programs will have the largest contributions to the Solomonoff prior. So let's say something about IXI then. Well, IXI is uses Solomonoff induction. So how does it work? It's an agent framework where at every time step an agent makes an action and receives the observation and reward. So it is modeled as two Turing machines, which an agent makes an action A4 here, you will see in the arrow, and the arrow, the action is an input to the environment. The environment is also a Turing machine, which takes actions and gives back observations and rewards. You can view it as if you see an image at every point in time, your image comes to your senses, and this is what the environment delivers you. It provides. It's a machine that provides you with those images, and you take in those images and compute internally the next action, and it goes like this. So let me give you an example. Let's say you want this. So the full expression of IXI is here, this big formula above there. I mean, it looks quite complicated at first, but in fact, it's not that much. So what happens is there is on the right, you will see the familiar already.
Has anybody experienced freezing,
Yeah.
Arthur?
Yeah.
Yes.
Okay.
Yes, I have too. I have.
Probably as Wi-Fi might be slow. Why don't we just wait for a minute? Oh, it looks like we lost him.
Are you able to message him?
He may have to log back in again.
Yeah. Why don't we hang tight for a second? I'll see if I can.
Well, I'm learning some stuff from this presentation. So
Yeah, the IXI formula.
Yeah, this is good.
You get the feeling. Oh, there, Arthur. Looks like you disappeared. Can you? You're still muted.
Yes. Can you hear me now?
Yeah, yeah. Unfortunately, your screen froze up, and then it looks like it crashed.
Oh, I'm sorry. At which point did it happen?
Right when you're dealing with the IXI, right? That's it. Which is very clear, by the way.
Okay. So I was about to explain that formula. So what you see here is at time slot k, an action k, ak is selected by this formula. And that's what you need to act intelligently. At every time point, you need to determine which actions the agent has to take. And on the right side, you see the Solomonoff prior, which looks at every program's queue executed on the universal machine U, together with the actions which you have taken before and might take in future, in order to output the whole history of what you have ever seen, the observations and rewards that you have received in the past, together with observations and rewards that you might get in future. So if you take a string like that and look at all programs that might compute it, the short ones will dominate, and those will be have a high probability. And if you this is essentially the probability that a particular history and an imagined future will happen. Now, which imagined future? one that involves these rewards. So the sum of those rewards are computed and multiplied by the probability. So what you have here is an expected reward, essentially. So for every possible future, you imagine all possible futures that might happen up to current times, from current time step k up to future time step m. This is called the horizon. And you look at all futures that might happen and compute the expected reward that you will get for each of those futures. For each of the actions that you might take, you compute the expected reward this way. And since you have an optimal predictor, which the Solomonoff prior is, you will be able to predict the rewards that will happen given the past rewards, and you will also be able to predict the future observations given the past observations. And then when you maximize this, all of this, you will get the optimal action. So to give you an example, well, I think I should skip the example. The essence about it is that this is a theory that actually demonstrates maximal intelligence. And this is proven formally by Markus Hutter. And if you can make that agent work, we will actually have reached AGI.
Quick question. This is for partially observable or fully observable worlds?
All this works everywhere. So for partially observable worlds as well. So you don't even assume to have states here. You have just observations, right? So there's no Markov assumption, no fully observable assumption. That's the most general reinforcement learning framework that you can imagine.
Does it work for multiple rewards or the reward distribution changing over time?
You don't actually. So the reward distribution can change over time because it's let's say the true environment is a semi-computable, semi-measured, formally spoken, but you can look at it as a probability distribution. But it's the probability distribution over infinite strings. So it's a probability distribution of all paths that might happen at all. So it's not over states, for example, or possible rewards. It's a combination of observations and rewards in all their combinations, in all their paths, essentially. So it can change as often as you like.
I see. As long as there's a computable method to determine rewards for a given sequence.
It doesn't have to be computable. It's, as I said, but it has to be semi-computable.
Okay.
But yeah, that's the condition.
Got it.
So, of course, this is far not enough. This very short overview is far not enough in order to give an introduction to IXE. But the gist of here is that in order to make it work, you need to make compression work. So, and because you have the 2 to the minus L. And this is what many people underestimate, let's say when you do machine learning and you choose a representation that is 1 bit longer. Well, who cares about 1 bit? Well, Solomonoff price says that the a priori probability that you have picked the right model will drop by a factor of 2 if you pick 1 bit longer. So you really have to take it seriously, and I think it could solve many of our problems. Later on, I will give you some examples of that. So what our contribution then has been is to develop a way to solve compression in all generality, or at least an attempt to do that. The idea is if you have all sorts of strings, you want to find the shortest description of them. How should you go about it? And the paper, well, we had a paper a few years before, but last year appeared a large exposition of the theory with all details. You can look it up there. So the main idea is the following: you have an object encoding, as a binary string of zeros and ones, let's say. And well, in practice, if you perceive objects and we find descriptions of them, you specify some feature of them, some property, like specify the size and the shape, and say, okay, it's a red object and it's positioned someplace in space. So often it's a string of properties that the object has, and intuitively these are independent of them. If you know the color of that object, it says you nothing about the shape. And they are both don't tell you anything about the location. So these are parts of the description that are independently of each other. And reminding you, the task of compression is to find the shortest description. So incremental compression finds those pieces piece by piece, step by step. So it finds first the size, for example, of an object, and then it maps out, it projects out the size from the string, and you get a residual description which describes the object up to its size. So it's an abstract way of describing the object, but mapping out the size. And then you map out the shape and the color and so on. And every time you do that, your description becomes shorter. And that's how you compress it incrementally. And because, well, how does it work? So if you use universal search, for example, you look through all programs that generate a particular string. Then you will be very slow. But if you do it piecewise, as I said, it can be much faster. And how does it work? Well, essentially, it's a stacked autoencoder, right? People working with neural networks know what I'm talking about. So you have a pair of functions, essentially. One is called descriptive map, and the other one is called a feature. And you have a string x, then you look for a pair of functions that changes that string to a shorter string. And then you have compressed a little bit. And you look for another pair of functions, and you compress a little more and a little more. So if the search for those functions is not expensive, if you don't have to look for long, then you will have an efficient compression method. That's the main idea. And it should work for all strings that actually possess properties. So in more detail, so you have to find Turing machines, F and F prime, that are reverse of each other, so that they are autoencoders, so they can recreate the string X, and also the description that you have achieved will be smaller than the original description. So we asked the question, what will happen if you take the shortest feature? So that means if you try to find not some complex regularity in the string, but the simplest as you can see, as you can find. And it has turned out, if you do it this way, then first of all, this feature itself becomes incompressible. So the homograph complexity of the feature, it is Turing machine, but it can be encoded as a string too. So the homograph complexity of that feature is roughly corresponds to the length of the feature. So you cannot compress it anymore. And And the second result was that the feature and the residual that you the remaining that you have mapped out, those descriptions they decompose into independent parts. So it's essentially the information content of X breaks down, decomposes into the description of F, which is incompressible, and the description R, which you can keep describing further. So essentially what it means that you have reduced the length of your string while splitting up the description into one little slice and the residual. And then what you do is you repeat the same story again with the residual. You find the next feature of the residual, and then you have a second residual, and so on and so on. And what will happen is it's like the information inside X will be broken down like a cake into different pieces.
I think we have a question from Stephen.
Yes.
Yeah, if it's allowed to interrupt shortly. Do you have a proposal of how to find the place where to start the compression? Like what I mean is that the external world is like a large pool of random data. And in that random data, there's something which is not random, which is a pattern. And a pattern is defined by that it repeats either in time, that you see it multiple times in succession, or that you see it in multiple places. But have you ever thought about a general method of deciding at which point in the data to start the compression? So where to take the first puzzle pieces from to put the big puzzle together?
You mean where in space essentially, or where in the data to start first?
Yes.
Oh, well, what I tend to think is, I'm not sure about it, but I think the world is some sort of a structure fractal, for a lack of a better word. That means that in wherever you look, you will see structure. Wherever in the data, well, there are some random parts too, but they're intermingled most often with regular parts. So if wherever you zoom into, you will see regularity in the actual world. Of course, you can make artificial data which begins with a long random string. Then, in that case, the search for the feature will be long. That's true. Well, but still, if it breaks down into different parts of regular and random, it will be faster than universal search. So the answer to your question is I don't think that it matters much in practice. You start where you start at some initial point and search for a description. The problem is if you want to look somewhere else, you have to compute that location from your starting point, which is also will be part of the feature. Because whatever you do, you have to compute it. You have to compute your search locations. So that's basically the answer.
Could
Okay, thank you.
Could one rule of thumb for the search be you start with shorter sequences? That way you're capturing sort of the high frequency information first, and then that allows you to build up your hierarchy.
Well, the idea is that you have one given sequence, not many to choose from.
But subsequences, I mean.
Subsequence.
Right. So.
Yes, you can pick a prefix, for example, of your sequence, and try to compress it. Right, which is one of the ways to do it. I mean, if your sequences are data points, like in linear regression, you might want to represent the sequence as a sum of two other sequences, and not as a concatenation or so. So you wouldn't take pieces of your string, but represent the whole string as a sum of two other strings, both of which you have a shorter description of. So this is a different way to decompose your data. But the idea is that whatever you take a concatenation or a sum, you will have to decompose it somehow.
Okay, so more a mixture model than a sequential model then.
Well, in a mixture model, you can also try to find the components of the mixture step by step.
True. Yeah.
I'm not sure. Well, if you wonder how it works, the essential idea is if you start with a string x, or the information about x is here in the black box, from like visualized in the black box, and if you can compute it from a feature f and the residual r, then the information of x will be inside the union of f and r, because it can be computed from them. But f and r might have some more information than it's inside x. And the idea is to prove that it's not the case. So in the proof strategy, I've essentially said that they shown that they do not overlap. F and R have independent information. And then I've shown that these outer parts, these superfluous parts, also do not exist if you pick the shortest feature, and you get the image like this. And then I've shown that the shortest feature is not compressible. You will get this. And in the end, if you repeat that, the information inside X breaks down into pieces. So essentially, what I found is a decomposition of algorithmic space, so to speak, that makes the search much faster. And what they call Mogarov complexity is in the end given by the sum of the lengths of the features and the shortest description of the residual that might be incompressible, like some noise, for example. So without going further deeper into that, but you can ask, of course, later if you like to. So what we found here is that the theory should be much faster than non-incremental compression, because it finds these features step by step, piece by piece, instead of looking for all of them at once. So in the last part of the talk, let me tell you about William. That's how we call the algorithm that actually tries out the theory in practice, so that you can get an idea how it can be implemented actually. And what we have here is a bipartite directed acyclic hypergraph. So essentially, it looks. You have the data 100, for example. It's like a string. It can be also arbitrary, various native Python data types, like strings, lists, sets, and so on, or mere numbers, like here the 100 in the blue box. And you try to find a description of it. So like a multiplication between 4 and 25, and the last one is an addition. So it's a DAG, right? A directed acyclic graph, and it's a hypergraph in the sense that in every operator here, another graph can sit inside. So you can have this whole graph computes a function, right? And this function can be inside each of those functions here. So you can do that, and in that way reuse functions that have proven to be useful, for example. And so just an example. let's say you have a list of ones, and a possible solution is in Python writing, repeat that 1 8 times, or do something more complicated. So we measure compression by looking at the default description length of those data. So we have a default description length of the list of ones, and then we have the description length of an 8 and 1 and what it takes to put it in brackets and that kind of information described as a binary string. So the default description of the original data is larger than the default description of the new data, the compressed data, then we have compressed, right? That's how it works. So let's say an example, we have a list beginning with 11s, and then it increases, and then it's constant again. William then might find a function like this, which consists of 2 operators, where it says, okay, there is from the range from index 6 to 11, from index 0 to 6, write an 11, and then leave everything else as is. That's what we just talked about, where it looks at the prefix, compresses it, and everything else is just left as is, and it's left for the next step. And in the next step, it compresses this part, and in the last step it compresses the 8s, and so the residual description in the end is much shorter than the original description. So essentially it's a depth, it's a tree of depth 6, which will be hard to find when you use exhaustive search, but in this way it finds the tree much quicker. So here is another example where you have simple figures like lines and triangles represented as lists of tuples, like that denote the coordinates of those pixels. So these lists of tuples can then be compressed well by the algorithm. So some rudimentary perception is possible by doing this.
Just curious, what kind of programs do these figures generate?
What do you mean by what kind of programs?
So for just like in the previous slide, we saw program, how it synthesizes the program.
Yes.
What does the final program look like for these kind of two-dimensional data sets?
For these examples,
yeah.
Well, unfortunately, I haven't printed them out here. Let me see. Well, what he does there is in Python the so-called zip function, where he first tears apart the x's and the y's into separate lists, and then he can compress the x's and the y's as some constant numbers or increasing numbers, for example, and also noticing that at the 8 edges, at the corners, they fit together, and it also notices that some coordinates are not far apart from each other, so it encodes it rather prefers to encode the difference between the coordinates rather than the absolute values, because smaller numbers take up less space. So, but probably you want to ask whether it actually consists of the lines, and whether it's a composition of a square and a triangle, something like that.
Yeah, I was just curious, like what type of representation does it come up with at the end?
Yes, what I said is it's a bunch of operators like zip and concat and stuff like that. The reason why it doesn't come up with lines and squares is because I haven't programmed a memory into it. So for example, if we, on the left side, if I had seen a line, it finds a representation of a line and it puts it into a composite operator that can be reused as a block essentially for other descriptions. Then it would find the description of the house on the right as a composition of lines. But that's still something to be implemented.
Okay. I'm not sure whether you go into this later in the presentation, but I would also be curious to understand your thoughts on how it might handle variations. Like, for example, the particular way the particular way this data is encoded. If you say give it a shuffled input instead of these points being ordered in a specific way, if they are shuffled, would it handle them? What kind of transformations can it deal with, or how it might deal with transformations? Those are very interesting.
Well, yes. I will give more examples now, and you will see it better. It's essentially what it will have is, let's say you have a line points, but the coordinates of points, but they are shuffled. What it will start is with one point, and then try to represent it as a line starting from the point and ending with the same point. And then it will try to change the end coordinates. Say, okay, let's say, suppose the line goes in some direction, and sees whether it can find the point that actually matches this prediction. And if it finds the point, it will extend the line. The more of a line it sees, the more it's compelled to look into that direction of search. And that way it will find even those shuffled points. It will essentially unshuffle the shuffled points.
Interesting, very interesting.
So yeah, you will see more how it works later on. So I think I will skip that. But here's an example of how it plays tic-tac-toe. So I've combined William with IXE with a reinforcement learning part, and then it can play tic-tac-toe in the following way. Let's say you encode the position of tic-tac-toes as a list of strings, as you see here below. Strings of length 1 can be either a slash or a minus, nothing, an O or an X or so. And then and the encoded moves are on the position 4, 1, 7, 5, and 6, and so on, the position of the move made. And the function that William has found is this reduce set item and so on. So essentially what it has found is start with a list of nothings, list of these minuses, and then at the position 4 insert an X, then insert at the position 1 an O, at position 7 an X, and so on. And it does that cumulatively. So it produces this whole list of strings, lists of strings. That's the whole history of this game that I have shown here on the slide. And having found that function, it has actually compressed this list of encoded positions because it's now shorter, and that means it has noticed the regularity that at every time step there's some X or an O added, and that's how the positions differ from each other. And what IXE then does is to look at different inputs to that function, and tries to extend that list of moves. So it looks what kind of inputs it can have, and that's basically considering all kinds of future positions. And having gone through all kinds of positions up to horizon 2, like two moves ahead, 2 moves by the agent, 2 moves by the opponent, it gets a reward, and the expectimax algorithm can then maximize the reward. And it plays tic-tac-toe, and as you see, that's the move we found at last, which is a fork, which is undefendable then. So it makes a smart move in playing tic-tac-toe. Of course, after chess and Go and StarCraft, and it's not impressive for anyone to see an algorithm playing tic-tac-toe. But I want to stress is that that this is without any training, so it can play, I assume, optimally right in the first game after seeing like 2 or 3 positions or so, because it can compress it right away. And that's also an answer how to approach one-shot learning. If you compress well enough, you can learn very quickly. So, okay, let's keep going. Let's look at another example, like outlier detection. So you wanted to see some programs. Now you will see some of them. So you have a list of A's, and interspersed there's 1 B out there. So the default description length is 244 bits, and finds a little program that essentially say, okay, repeat A 26 times, which is a clean repetition, and then insert a B at the 18th index. And the description length of the program will be the sum of the descriptions of the leaves here, and plus the description of the operators that you need. And what you come up with is a compression rate of 80%. And as you see here, the outlier gets detected essentially. So inside the representation, you have this clean string of A's, which is actually some sort of denoising. So denoising is something that that is automatically a consequence of compression. So some people wonder, what about lossy compression, right? I find always an ideal description. Well, lossy compression is an easy consequence of lossless compression. Because in the lossless compression, if you do it well, then the regular part and the noisy part will decompose. So you will have, your representation will split into a regular and a noisy part. And if it splits, you can just throw it away. For example, the noisy part would be the 18 and the B and the Z item. You can just throw them away and keep the clean part. Let's look at linear regression. Let's say you have 2 arrays given here, the Y's and the X's, and they have both some description length. And what William does is then it doesn't care about inputs, outputs. For William, he just wants to compress the data that it gets. That's all it does. So if he finds a way to compute Y from X or compute X from Y, then he has already compressed, because he doesn't have to describe both separately. He describes once and computes the other from it. So that's what happens. Well, first he says, why don't I subtract just the 1 from my array of Y's? And the dashed red line is his current estimate, so to speak, of the data. And then he says, okay, how about I change the 1 to a 2? And then he changed it to a 4 and changed it to a 16. Now, keep in mind, this is not a built-in optimization algorithm that does that. It starts with a 1. That's, I give him the number 1, and then he has the operators like add, addition, multiplication, and he adding a 1 to itself, and then adding it again to itself, he generates the numbers that he uses during this optimization. So this incremental compression algorithm generates its own estimates, so to speak, so its own attempts. So then, after having subtracted, is what happens here is actually he has centralized the y's. He has subtracted something roughly the mean of them. He subtracted, and then he says, "Okay, let's use the x." And so x added with some residual plus 16 is y. So the residual is something that still contains information, right? We will try to compress it further then. And you see the estimate is already improved. And then he compresses further, like just in the sense of incremental compression. What he has at the leaves, at the bottleneck, so to speak, of this graph, he keeps going, and he says, okay, he uses x twice, which is some x prime is some changed version of x, and then what the dashed line is essentially 2x plus 17, and he is almost done because the correct description is 2x plus 18, which he finds then in the next step. Yes. So, and the prediction is done. And on the below on the left, you will see the noise. And this is also an example of denoising, essentially, right? The separation of signal and noise is done this way. You can look at different examples like classification. Let's say you have some values x, and the violet ones are in one class, like true, and the other ones are in the false class in the binary classification example, as we see here on the left. And what he finds there, he again centralizes. He just subtracts some number from the x's. So he centralizes again, subtracts 4, and then in the end, he says, okay, from the residual, everything that's smaller than 1 has to be in one class. And there is a prediction error. Well, you might wonder, how does it work? Why is the prediction error small here? The description length is 454, and the original is large. Well, because the prediction error has a true entrance wherever the prediction is wrong. And if there are few of them, the description of the binary array will be short, because you can just point at the indices of the wrong prediction, and that's it. You have described it. So that's an example how he does classification. Yeah, we have also a decision tree example. Well, I think I shouldn't go further deeper into that. The idea is to give you to give you an idea that machine learning algorithms, most often what they do is actually data compression. But in the decision tree, for example, there's usually you try to minimize the Gini coefficients, the diversity of the elements in the sets that you get. But if the elements are not so diverse, you don't need so much description. The length of your description will be shorter. You'll just say, okay, it consists of this and this and this element, and point to the indices, for example, and then you're done. So this is actually taken from the Python standard example of classifying flowers, Setosa, versicolor, and Virginica. So yeah, let's keep further. So further examples I want to demonstrate later on at some point. So clustering, collaborative filtering, maximum likelihood, and so on. So let's move slowly to the end. And well, this is a fairly complex slide. I think this will be overkill. But the idea is that the different, we can start with IXI, and we can use the theory of incremental compression to start to break it down mathematically too. And if you do that, I have given a talk at the last at the AGI conference 2 years ago, where you can reformulate IXI in a different way, and using so-called renormalization. And what emerges there is some type of attention mechanism. So it starts to look at the more relevant part of its environment. And the slide here is to give an idea how various psychological cognitive functions might emerge when you try to change IXI and break it down to make it computable, to make it more efficient, and to find an approximation that works better. And so the hope is that various cognitive functions might emerge from there. But this is a long path, and we've just begun to do this. So in summary, I have presented you a systematic approach to AGI, first starting with some psychological examples, and then I've presented you the theory behind it, which is based. Can start with IXI, doesn't have to. It's just a comfortable mathematical proof that what we are dealing with will actually lead to intelligent behavior. And then I've presented you our theory of incremental compression and the way it works in practice with the William algorithm. So we could maybe, right, with a big maybe, regard human cognition even as IXI under resource constraints. So, with William in the end, we have demonstrated some successful results. Later on, we will. What we're planning to do is to make it work better and better, so that, for example, William can start to generalize machine learning algorithms, and then you can use it. Just take your data, feed it to William, and it will generate predictions for you. Essentially, some sort of automatization of machine learning, but as opposed to AutoML, using a completely new idea. So hopefully I was able to present the approach more or less understandably, and for me it was a big discovery to study algorithmic information theory, because I think it's the language of intelligence essentially. If you want to think about intelligence and what happens there in the mind of humans, you need a language, a way to think about it. And if you want to build artificial intelligence, then you need a mathematical way to do it. And algorithmic information theory is a great way to do that. And the late Marvin Minsky actually said in his last appearance on a discussion that everybody should learn all about it and spend the rest of their lives working with it, which he said jokingly, half jokingly. I think it was half jokingly, but I think it's very important. Yeah. So thank you for your attention.
Thanks a lot, Arthur. And by the way, I'll have this recorded, so I personally I'm gonna rewatch. But most of it made sense. But I I need to watch it again, I think.
Great. So yeah, I'm happy to take questions.
I can go. First of all, thank you so much for a wonderful talk. I mean, it was amazing. You laid out your theory really well. With examples helped as well. So my question is, the, how would this apply to higher dimensional data, say image recognition or any high dimensional data? It seems like I mean, from my naive understanding, listening to you describe it, uh, it might not. I mean, it might not be efficient enough to find a solution for high dimensional data. Can you talk a little bit about it? See if I understood it.
Well, the thing is this: when you do machine learning for particular tasks, you know the task in advance, and you can already choose your algorithm in such a way that it will be efficient for that type of data. The big conundrum in AGI is that you have to make an algorithm that solves problems that you don't know in advance. So, and the big conundrum is whether this is possible efficiently at all. And I think and what is lurking there is, of course, the curse of dimensionality. And the great sort of, well, I consider it as a breakthrough, I would say, as a big advancement is that you can actually take any such problem and find an incremental approach to it. And and there was this result that the Kolmogorov complexity is the sum of the features. And this algorithm, you don't have to backtrack. You never have to go back after. You have compressed a little bit, and then furthermore, you don't have to go back and find some different way because you're caught up in the dead end, because there are no dead ends. And that's the surprising part about it. There are no dead ends in this approach. And so your question whether it works for some complex high-dimensional data essentially comes down to the question whether this data consists of regularities that are small enough. So if let's say you have a data set which is compressible, but it does not consist of pieces. Then incremental compression is not applicable. But to be honest, in the last 5 years of the theory, I haven't found a single example of such a data set. Because not having features meaning not having properties. So you need a data set without properties. Which is not random, but still compressible. I think it's a hard thing to do. So where it will be possible but slow is where the features are long. For example, where you have a data set which consists of random data, but somewhere far away, there is a regularity. Let's say we would live not on the planet we live in, but in some random noise. But the next regularity is the next galaxy or so. We'd have to travel to the next galaxy to find the next regularity. Then it's not possible. But it seems that our world is teeming with features, even if it's a high-dimensional data. If it's like an image data, you always have surfaces that are filmed more or less with uniform color, for example. Finding those surfaces already compresses your data, and you will compress optimally when you find where the surfaces end, which at the edges of the surface. So you will find that an object, let's say this phone, you will find the edges because you will have to find the average color value in order to subtract it from the data. And therefore you will find the edges of the phone for optimal compression. And after having found that, you may have my face, you will also have to find those features. And maybe other features of my face will have a different colors. So you will actually find the parts that the objects actually consists of, like the nose, the eyes, and so on. These part-whole composition of an image will be the consequence of compression. And I don't think it will be much more difficult than the examples I have shown you, because you can just start with some corner of an image and you see a white space there. You fill the white space, and then you find something here in the middle in the face. You fill it with something else, and you compose these things together. Everything can be done step by step. That's why I think it should work also.
Hi, may I ask a quick question? I appreciate your answer. When dealing with the notion of AGI, we actually think of multimodal input from multiple sensors, not just one sensor, not just a camera, but maybe camera. If you're dealing with a telephone, a cell phone, which might be the input device, then you'd have a gyroscope in the telephone. You'd have a Wi-Fi signal.
Yes.
You'd have power, energy measure, and so on. If you're dealing with a robot, you'd have many more sensors and monitors on the device. So we're going to get multi-dimensional inputs coming in. Now, are you familiar with any of Carl Friston's work?
Yes, a little bit.
Okay, so you're going to get a lot of sensory information coming in, but then you're going to also have some decision making or action selection coming in. And from what I saw so far, what I understand as far as the compression is concerned, I didn't see anywhere where you have action selection. Or are you going to have to run the algorithm in not only on these different sensory modalities, but also in the domain of action selection as well?
Mm-hmm.
Is that the case? Can you address that?
Sure. So let me share the screen once again. As I've written here, compression is not a panacea for everything, and I've mentioned this other work where attention and action selection in the talk 2 years ago was addressed. So I think action selection is part of the things that need to be solved yet. So in terms of IXE, if you look at it, so here the action selection is already solved. It's done by this Expectimax search, and the part I have solved is the induction or the compression part. So you are right. Action selection is not part of the compression solution. So, and which is a difficult conundrum, and there are big questions. For example, are the rewards at all given from externally, or do we need some intrinsic reward? Yeah, there are also exploitation questions and delayed reward questions, which are not touched by the compression story.
I'm curious. I don't know if you're familiar with like DeepMind's vector quantized variational autoencoders.
Not sure what you mean. Variational autoencoders in general, yes, but what do you mean by DeepMind?
They have it's called VQ Bay2, which is it's an autoencoder, but they vector quantize the middle layer, and it's taken from like JPEG inspiration from JPEG compression. But what it can do is like compress, well, it can generate realistic face photos and whatnot.
Yes. Yes.
So I'm just trying to see, I come from more ML background. I'm wondering, like, what is the benefit of your approach versus like a general ML autoencoder?
The thing is, I have a very critical stance toward neural networks because I think neural networks have difficulties to generalize. I mean, it's quite provocative to say it like this, but what I mean by generalize is extrapolation. So in neural network, people call it out of distribution generalization, right? You will be familiar with it. And it's a big conundrum and big question how we can generalize beyond the training distribution, which is something people do all the time. And I think the reason is that the systems there don't compress well enough. And in order to compress well enough, they would have to actually recognize or map the structure of the representation, which is a neural net, should somehow match the structure of the world. What I mean by that, if there is a table and a chair outside, you should have a representation of a chair and a representation of a table, separate and not intermingled. In the neural net, it's often intermingled, and which is bad for compression, it's bad for generalization. And of course, in order to solve the out of distribution translation problem, which would be involved if you change the position of the chair independently of the table, for example, you need to compress well enough. So I think the contribution to this ML world is that some of the big conundrums of current, let's say, neural network research can be addressed by those ideas. So some people have tried to build in algorithmic elements into neural networks, like the neural Turing machines. You have probably heard about it. And I think the development of research should go into that direction. There should be more diversity of computational elements, not just sigmoid or ReLU units or big bunch of the same units. There should be different computational elements that should be free to connect, to compose with each other, and not be somehow connected in a fixed way, which is usually done in neural nets. And it should always compress better. Like in an autoencoder, it's also layer by layer, right? But the width of the space of the functions that you draw from is too narrow. You use the same neurons everywhere, and so you find essentially in my language, the features that you find during incremental compressions are too large, and therefore they don't become independent of each other, and your whole representation becomes too large, and therefore the mutual information between those layers becomes too large, and everything gets intermingled and gets less interpretable. It's also a part. Well, maybe that was fairly confusing what I said.
That's one of the, I think one of the bigger things the ML community is working on right now is that, outer distribution representation and like disentangling the features. So.
Yes, well, Solomonov induction has solved in theory. We know what we have to do. If you compress optimally, you will predict optimally. So you will also predict out of your distribution. Full stop.
I just wanted to add that, I mean, explainability is a hot topic these days, and it looks like your approach is pretty well explainable.
Yes. I think that's also related with that. That's what I've said. If you have a representation that decomposes in the way that the world decomposes, like I have said with the chairs and tables example, then you will also have explainability, because your program will have consists of parts that corresponds to chairs and tables and floors and so on. Because we can also see evidence from language that we often use words that map onto those objects. And so most likely from the representation that we will get from optimal compression, it will decompose into pieces for which we already have words, if we look at our visual scene or so. So that's what makes the approach more likely to be explainable also.
I had a question. Do you think there's a the strategy is to look for the shortest feature first, but do you think there's an inherent relationship between the shortest feature and its generality, perhaps? I mean, the short is what I was thinking of was, I mean, is it possible that being shorter means being more general? Or
it means that being shorter means that you are less likely to get superfluous information into your description. So if you have superfluous information in your description, your prediction will get worse, because your program is just noisy, essentially. And if you pick the shortest one, you will remove everything that might be unnecessary and redundant. You will remove everything, and that's what will optimize your predictions, and by inference also optimize your generalization.
it seems like after a while, if you ran it on lots and lots of cases, perhaps the shortest, and I'd wonder if the shortest features are the most general. But
well, in particular cases, it depends on the task. I mean, if you show him an image of a right angle, but you actually mean a normal angle, but he recognizes the regularity of the right angle, then he will compress more than it's necessary, because you meant some typical typical triangle. So you will have to show him several examples of what you mean, and then he will generalize more properly. But it's in some sense not his fault if he recognizes the regularities that you have not meant. I mean, I'm not sure whether this addresses your question. Maybe you can give an example where of generalization.
let me think about that for a minute.
Okay.
If I may ask, so if you're, let's take an example. You've gone through and you've got several cases, and you find that you get a consistent first compression among the various cases. Is there some method that you would suggest, or perhaps think that it's worthwhile to say, since on this first case, I had a certain kind of compression, and it gave a first kind of result, that if I could short circuit later cases that had that first kind of compression. So in a sense, you've got a compression on a compression, if you will, where you're using the first set of cases to help determine what kinds of compressions you would want on the later cases, and therefore speed the whole process. Is something like that possible, or is that you think that's possible? Yeah, do you think it's possible?
Well, the thing is this: if you have different cases that have common information that are compressible by the same function, for example, then the actual task that you are looking at is the is the whole history of your data. In ICSI, it's the whole life history from birth until now. Whatever you have seen, you want to compress. So it's not like you want to compress a single frame that you see now. It's also in four-dimensional in time. This four-dimensional data set is something you want to compress. And reusing of already successful things is essentially an approximation of the fact that we don't know the future. So we would like to compress our whole life until we die, but we don't know the future. So we make sort of proxies. We sort of remember what we have seen before in order to reuse it later, in the hope that the future will not have too much new information, which is often the case, I mean, to some extent. And then you can reuse. So it's a property of the world that you can actually reuse things. And in practice, this is something I'm planning to do, which is one of the next things actually to set up a memory where the useful functions that have been found before are stored and can be reused with a higher probability than other functions. So I'm not sure whether I have really answered your question.
Yeah, to some extent and stuff. I mean, I have some practical applications for something like this. So, but I'm not sure how to actually apply it. Truth be told, I'm a lawyer, and I'm
Okay.
trying to apply this to court decisions and court opinions. And and so because a lot of what you see in a court opinion is kind of the initial stuff is always jurisdiction, and then there's a set of facts, and then there's the actual discussion of the law to the facts, and it's that third part that everybody wants to get. And so you want to have an idea of what the facts are, and those would be something that would be compressed, and the jurisdiction's almost immediately compressed because it's very, very common and comes up almost universally. So it's the set of facts. So you want to pick out certain things within the facts to classify what the case is, and then look at what the discussion is. But there's an aspect of philosophy called neo-pragmatism, which says basically people interact through language, and since law is the regulation of actions between people, the neo-pragmatism and that theory can be applied with what you just went over to get some type of overall neo-pragmatic legal what's called critical legal theory of Carl Llewellyn and Richard Rorty and some other people like that. And so that's why I'm here listening. And so I was wondering if, since so much of a court opinion happens again and again, could you run through a bunch of cases through a set of algorithms, find that first initial set of compression, and then just, essentially when you get a new case, you skip that whole part and really focus on the meat of what the opinion's about, because that would save an enormous amount of computation. And that's a big part of what we're trying to do.
I'm not sure I really understand that you have cases where you have common parts between the cases, and it would be nice to recognize them, and that somehow will make things quicker in the future.
Right. Well, right. So essentially, you would skip that part and then make your data. That would be essentially the first compression, because you're skipping a lot of stuff you're not going to be interested in. And so that would reduce the data set considerably.
Yes. Well, that may be an application for natural language processing, because they're written in words, right?
Right.
And find out common regularities between those cases. I mean, it's of course also difficult because there might be synonyms or so. Different words meaning the same, or different sentences meaning the same.
Right. Well, there are terms of art, and those are outliers to the general language, but they're consistent. In fact, and the problem with law is that law changes, and so cases that you read earlier in your life, if you will, are no longer applicable. So those are things that you need to find so that you can essentially correct the thinking. So so your client wants to know what the law is, not what the law was, and that's what's used for the prediction. So there comes a point where a lot of past data is no longer applicable.
Yes.
It's no longer helpful. So, what you said about, the full compression from, beginning to end, that doesn't work in law. Usually once a case is about 3 years old, it's pretty much, unless it's a major case.
Well, I mean, if you have a data set which is homogeneous in the first, and then also homogeneous in the latter part, but it changes radically in between.
Right.
You can also compress it all together, but then your description will just decompose in two parts. So this should not pose a problem. But what's more problematic is, of course, representation of language. And I'm currently in the AGI context in favor of course, connecting the language to the actual world that we live around, and not just dealing with word corpuses, because you then get into all sorts of problems. But I think your task would be better dealt with NLP algorithms, which could be tailored to the case that you have.
What about like, I'm looking into like program synthesis, like synthesizing Python code or programming by example. I don't know if you look at like flash fill in Excel and whatnot. I'm wondering if your algorithm could possibly be used in programming by example, where you give examples of a transition and then it would ideally generate.
Yes, I mean it's an advancement in inductive programming. That's exactly what you're talking about, and it could help test-driven development, for example, where somebody writes a little test case with different examples, and then William could induce the program for it. I think it's essentially what it already does. I mean, the graph that it induces is already a Python program. I mean, you could write it not as a graph, but as a program. It would be just Python code. And if I implement this reusing of composites and instead of primitive operators, then you will actually have functions which consists of other functions and so on. So you will get regular Python code essentially, but you would have to expand it to more data types and stuff like that.
Do you have a paper I could read on that? On your approach?
On William generally, or on that particular example?
I guess, yeah, William.
Sure. Just go to our homepage, occam.com.ua. I can put it
in the chat.
In the chat, I posted a link to the Alice.
Yes, there will be essentially two papers on William. Recommend the latter that has been published at the AGI conference. So yeah, they're all my papers, so you can download what you like. I'm planning actually to, in the next AGI conference, if it happens this year, I'm not sure, to publish these machine learning results. So there you'll be able to read more about it.
Do you have any stuff on GitHub or anything, like open source stuff?
No, we haven't put it open source because we want to find a way to finance this, because it's difficult to finance a whole lab from on our own. And the idea is to generate some spin-off companies that use that algorithm in order to yeah, to have some practical applications. This is something I would really love to have to not just to do theory, you know, or some demonstrations of code, but I would actually like to do something useful and be of help for somebody. And while on the way approaching toward AGI, that would be a great combination.
I was wondering how you were protecting your intellectual property if you were. So it sounds like a trade secret route, pretty much.
Well, we just don't publish the code.
Yeah.
That's the way how we protect it. And
Well, there's patents and you know,
No,
IBM
what-
and
yeah.
Microsoft are taking out patents. But
Right.
there's-
As an IP lawyer, what he described is a trade secret. And he's not
Yeah.
going to go to the patent route.
Right.
But there's issues about patentability, which is Section 101 of the Patent Act, at least in the US. And so whether or not something like that could be even patentable in the first place. And so this comes up quite a lot in AI type of patents and such. And so for a lot of my clients, I always recommend trying to take the trade secret route, which is exactly what he's doing by not publishing the code and then architecting the company such that the code had to be accessed through their API on their server and therefore never
Yes.
disclose the code. And
Yes.
that's a straight up trade secret route.
That's what
the idea is to make a service where what you just said, that people interacted somehow at some interface without having access to the code, but having the results of the computation. So I mean, it's a bit unfortunate because from a scientific perspective, I would love to share it, but from somehow sober, rational perspective, it has to grow somehow, and and without being jeopardized by somebody. And so that's the policy we're currently pursuing. By not publishing it.
It seems
The-
smart to me.
Sorry, the tests that you did, you've shown several examples like the OXO program. The data samples that you've shown, they are all having a Boolean match function. So the comparison returns true or false. Now in real life data, and then I'm thinking about visual patterns and audio patterns and a combination of them. There you have an analog return value. So you have a match function, which, for instance, returns an analog value between 0 and 1. But that changes the entire algorithm. Have you ever tried your algorithm with the match function, which returns an analog value?
Well, I'm not sure what you mean by analog, but you mean a real value instead of binary or so, instead of Boolean.
Yes,
right?
a floating point value.
Yes, I mean that's the example with regression. You have a noisy line, and your description is decomposed into a program that outputs the exact line plus the noise. So here, let me show it on the screen. Here you see it in the end. So the red line is what this part of the algorithm computes, and the noise around it is here on the left side below. So it actually decomposes into noise and the regular part, the whole description. So you don't have to match the data ideally. I had also a different example in year classification. You have a prediction of Boolean values, but they don't match everywhere, and you have a prediction error, which sometimes has these false true values in there, which indicates where the prediction was wrong. And yeah, so then there's no problem in dealing with such continuous match functions.
Yes, I admit it's not a problem, but it introduces an extra factor, and that is that you introduces doubt. So you have potentially multiple templates, stored templates, which matches. So for example, I see an animal and it looks a bit like a dog, but it also looks a bit like a cat. So then the program has to decide which of the two it is. And if it's a real world situation, then there's lots of doubt. So it's not just two patterns between there's doubt, but there are not infinite, but hundreds of patterns, which might be a match. And for such an algorithm, it's a challenge to decide intelligent which the exact template is to use. So whether there's a match with only one stored template or with multiple. And if there's a match with multiple templates, then there's also multiple reasonings to follow and multiple possible actions as follow-up step to execute.
Yes, yes. So this is the inherent uncertainty when doing induction. You can pick the shortest program, shortest description, or you can pick the second shortest. And ideally, you should find all short programs. And the long ones don't make sense, but if you find all short programs, then you will have among them the description of a dog and then another description of a cat. So currently, the theory from incremental compression is best when looking for some shortest program. But finding all the short ones is another task. And yeah, it's you're right. You should somehow go about how to systematically find those that appear less likely, for example. Yeah.
Also, is IID data the assumption for this algorithm? Like
No.
machine learning. So how, like for example, initially you see, let's say the final pattern looks like an L, or the actual joint probability looks like an L, but initially data only has is highly representative of just the vertical line, and then later on you receive some data that has the horizontal line. How like would this algorithm sort of capture that first, a program that generates vertical line first, and then when the data comes in for the horizontal line, add that in somehow and sort of make a composite?
You mean if the data comes in kind of stepwise, temporarily extended, if you don't have all the data at once?
Right.
So what will happen if, let's say, you have compressed the vertical line and then new data comes in, and he will try to reuse whatever program fragments he found useful before and reuse it in the novel data, and then try to compose them together. But as I said, this reuse is not implemented yet, so we don't deal yet with the task of incremental expanding of the data set. So this is something yet to be dealt with.
Okay, so in that sort of sense, it is, at least this iteration is restricted to within distribution generalization.
I'm not sure what you mean by that.
As in, you cannot provide evidence for change in distribution, and the algorithm can then realize that, oh, the actual distribution looks like something else, and that's how it then generalizes that, okay, this is the real distribution, and I'm going to start generalizing it that way.
Well, what you can always do is throw away what you have before and take the new piece and start compressing it all over again. You can always do that. And if it works well, it will do that efficiently. But if you want to approximate it and want to use some incremental composition of your description, let's say, then you will need a model of well, how frequently you assume that what you have seen before will come next, something like that. But the advantage is that since in incremental compression you have these shortest features, these features can be seen as something like atoms of information in quotation marks. So that means that everything you want to describe is composable by those atoms. It's like objects composed of atoms. Descriptions of objects are composed of features, of shortest features. And so then when something new comes, a feature is either part of it or it's not part of it. So you can essentially, you don't need to throw away everything you had before, because you can reuse pieces of them or not reuse them, but it's not like you will have to cut things in different ways or reuse other parts or something like that. That's the advantage that incremental compression brings for your case where with time the data changes.
Right. I mean, the reason that I bring that up is because that's posed generally as the challenge of lifelong learning that a real AGI agent would have to contend with.
Yes. Yes.
Well, it looks like we're pretty much out of time as far as what we had scheduled, and I don't want to hold you any longer, Arthur. Thanks a lot. This was really good. And
Thank you.
Thank you.
And,
thank you as well for inviting me. It was
well,
a pleasure talking here.
I'm glad you were willing to do it. And I'll post the recording to the event page a little bit later as soon as I get it done. And
Okay, sure.
If anybody has an idea for a topic they'd like to take on, let one of us know.
Yeah, so you can write me some other questions if you come up, or ideas, feel free.
Hey, thanks. I'm still, yeah, there's a lot to think about here.
Definitely, there are a whole bunch of ideas and many things to explore. It's curious times we live in.
Yeah.
Okay, well, I think I'll close it down now. Thanks a lot, everybody, and see you all next time.
Thank you.
See you. Bye-bye.
Bye.